on both the wave and the balanced flow evolution. This is a collaboration that involves multiple people. Gerardo Hernandez Dueñas, who's doing a sabbatical with us at NWRA right now, Leslie Smith in Wisconsin, Yanis Kuiper and Pascale Beauvais-Auberteau in Paris, and Jeffrey Early, my colleague at Northwest Research Associates. So the motivation for my talk is just trying to understand when gravity waves and balanced flows actually can exchange energies. There are many, many studies that point to the possibility that this happens, and I've just named a few here. I'm involved in one of these studies, the one with Gerardo and Leslie, published in 2021 in JPO. But then I'm also involved in two studies that show that, in fact, the balanced flow just acts as a catalyst in the evolution of wave fields. And so really the motivation for this talk is trying to understand how waves alter the evolution of balanced flows, and in turn, how balanced flows alter the evolution of waves. And in particular, what I'd like to focus on this time is what the dynamics of behind these two scenarios are, and can we understand these differences in terms of the impact of resonant versus non-resonant triad interactions. So that's the motivation for the talk. I will briefly just go over how we go about understanding these triad interactions. So we start with the full nonlinear Boussinesq equations and linearize them. And in the usual way, we can find then linear eigenmodes. And for the rotating or the F-plane Boussinesq equations, there are three linear eigenmodes. Two corresponds to internal waves, and the third corresponds to this V mode, which I'll just call it. I'm just saying ahead of time that at times I refer to it as the V mode, the geostrophic mode, the vortex mode, the balanced mode. It's also the slowly evolving mode, because as you can see, the frequency is 0 compared to the waves, which have high frequency. The V mode accounts for linear potential vorticity, here defined for constant stratification as just the linearized Ertel PV. The wave modes I also refer to as the fast modes, because they have frequencies that lie between F and N, away from the 0 frequency. And these wave modes have no signature on the linear PV. These eigenmodes form a complete basis, and so any flow can be decomposed in terms of them. If we go back to the nonlinear equation and express the nonlinear term, or actually the flux terms in the energy equation in terms of these three eigenmodes, you can see that there are 27 nonlinear triad interactions. Not all of them are active. Some of them actually are identically equal to 0. The vortex wave class does not play a role, but pretty much all triads can be understood as permutations of these three classes that involve three wave modes. So it's the projection of wave-wave interaction onto the wave eigenspace, or wave-wave vortical interactions, which could be interpreted as the projection of wave-wave interactions onto the vortex space, or the interaction of a wave with a vortex mode projected onto the wave eigenspace, etc. And then the vortex class, which represents just what it says, the interaction of three vortical modes. Okay, so I'm sure everybody is familiar with this, but just to set the stage, what do resonant triads do? Well, one thing they do is that they conserve linear potential vorticity. And so in that sense, there is no possible energy exchange between a vortical mode or between vortical flows and waves, because that would be a violation of this linear PV conservation, okay? So given three eigenmodes, and I've just denoted them here with their wave vectors K1, K2, and K3, the corresponding frequencies given by sigma 1, sigma 2, sigma 3. The resonance conditions are that the wave vectors must add, and in addition, the frequencies must add. That's pretty stringent, especially for wave-wave triads, especially in a numerical model, okay? One thing about resonant interactions are that they're strong. They have an order 1 impact on the flow evolution, and so they're often the ones that are taken into account, okay? So you can have wave-wave-wave resonant triads, and in that case, energy remains in the wave field, okay? Resonant triads involving two waves and a vortical mode. In this case, the vortical mode just acts as a catalyst and transfers energy between waves of equal frequency, okay? Oops. Yeah, going back to this. So, right. So that's actually one that is fairly easy to obtain, because any two waves with wave numbers, wave vectors K1 and K3, for example, will find a vortical mode with wave vector K2, and the frequency requirement is trivially satisfied. The other class of resonant triads, vortex, vortex, vortex triads, they're all resonant because the frequency requirement is just trivially satisfied in that case, okay? Now, what happens when you have non-resonant triads? Well, non-resonant triads don't conserve linear potential vorticity, and so that that opens the door to possible energy exchanges, okay? One thing about non-resonant triads is that they are weak compared to resonant triads, but they're numerous. In fact, most interactions, most nonlinear interactions are non-resonant. So going back to the three classes, again, wave triads, the energy remains in the wave field. Vortex triads, energy remains in the vortex field. But the one that is important for non-resonant triads is this wave vortex triad, where energy can now flow between the two eigenspaces. So I'd like to focus on two examples, one where you get non-resonant triads to be important, and the other where they aren't. So what I'd like to do is to introduce a tool that we've been using, reduced interaction models that were developed by Leslie Smith and collaborators over the years. And these models, what they do is that they, well, first of all, they include all resonant and non-resonant triads. They satisfy global energy conservation, but individual models remove certain classes of triads. So for example, QG, the QG we're all familiar with, only includes the vortical triads. There is no wave component in QG. And the characteristic of QG is that it leads to an inverse energy cascade. There's also a waves only model, which only includes wave triads. There's no vortical energy in this. And of course, it leads to a mostly forward energy cascade.
5 minutes left.
Oh, 5 minutes left? Okay. I think I will then just go on. Okay. Oops. So anyway, the truth model is the Boussinesq model. So this is this first example deals with a submesoscale flow. Okay, submesoscale flow spun up by random wave breaking events. I'm not going to go into details, just to say that the Berger number for this problem is 4. And when the model is spun up, oops, yeah, there's comparable vortical and wave energy in all 3 models. So just to remind you, full Boussinesq has all the interactions. This one is excludes wave interactions, and QG has no waves. Okay, and so you can see the differences in the different models. When you have QG, you have tight anticyclones, smooth filaments. When you exclude wave interactions, there is actually no tight vortex cores. And Boussinesq includes both the features of QG and also you can see presence of waves. And so, this actually kind of summarizes what happens in this case. And so in black is the QG model, dotted lines are the waves, and solid are the vortical mode. So you can see, and this represents the forcing. What you can see is that the vortical mode, let's see, yeah, the vortical mode energy really diverges at small scales. In green is the model that excludes wave interactions, and so you can see that the energy is actually flowing in through the only available nonlinear triad that it has, which is the wave vortex triad, and it overestimates the amount of vortical energy compared to the true Boussinesq model, which has more small-scale vortical energy than the QG. And so this is, I'm not going to have time to explain it, but this is actually due to non-resonant wave triad energies. So you can see that the non-resonant wave triads set the vortical mode energies at small scales. I think I'm just going to have to move on. If I just have, this has an impact for lateral dispersion. As you can see, you can, in QG, particles really remain inside tight cores, whereas in the Boussinesq, you can see the impact of the smaller vortices, which leads to greater lateral dispersion. Nothing happens in the wave model. So for lateral dispersion, vortex and wave interactions actually do matter, because you can see that compared to the Boussinesq model, you have stronger diffusivities. The second example that I was going to talk about, but I think I'm going to have no time, is an isolated mesoscale eddy perturbed by a wind burst, okay? So this was a study done in relation to the Cypress eddy, which is a quasi-permanent eddy in the, and so in this case, what we're doing is decomposing the vortex velocity, decomposing the velocity in terms of a slowly evolving field, and defining the fast velocity to be the difference of the total velocity and the vortex velocity, and further decomposing the fast velocity into inertial oscillations, which are just confined to the mixed layer. And then the wave part is the difference between the total fast and the inertial oscillations. Just going to play this little movie here. So this is an example. Okay, so up here is the vortex, which is essentially unperturbed over time. Here are the inertial oscillations, which are confined primarily to the upper part. And here's the wave. And so you can see that the wave time scale is definitely set by the inertial oscillations and the spatial scale by the vortex. But surprisingly, what we find is that this is the vortex energy over time. This is the near inertial energy over time and the wave energy. And you see that the vortex in this case acts entirely as a catalyst, which points to the impact of wave-wave vortex resonant triads, where there is no energy exchange. It looks here like there's a lot of near inertial energy, but bear in mind that this was that the vortex is confined to the very center of the domain, whereas the near inertial oscillations are everywhere. And from the wave vortex model that Jeffrey introduced, we can actually see that in fact the inertia-gravity wave energy comes entirely from the inertial oscillations and not from the geostrophic mode. So I think I'll just go to here. Here's another example that was shown by Jeffrey. Again, catalytic behavior, and so only resonant interactions. So for my conclusions, I'd like to just say that it's important to really take into account not just resonant interactions, but non-resonant interactions, because they're often neglected, but they're numerous and they're nonetheless important in setting the correct levels of energy at all scale, in both the vortical component and the wave component. Finally, I'd like to also say that our results are entirely consistent with those reported in Thomas and Daniel, who find enhanced dissipation of geostrophic energy in the presence of strong wave fields and no disruption to the inverse energy cascade when waves are weak, which is basically what we find. So enhanced dissipation means that there's an excess of vortical energy at small scales, which can then be dissipated. And when you have a weak field, as in the inertial oscillations at the top, you only have resonant interactions, which are the first ones to show up because they're the strongest. Thank you, and I'm sorry I underestimated how long it would take me.